Today we're going to take a close look at how the Earth is measured, how we understand its shape and its size, and then how we begin to take some of this data that we collect and map it out on the surface of this planet. As you can imagine, the concept of location is very important, especially when we're trying to take all of these many variables that we're observing and measuring and trying to systematically and scientifically categorize and classify them. So the shape and the size of the planet becomes important, how the planet interacts with the solar system and of course the sun. So the Sun-Earth relationship becomes important. And then how we depict all of that for ourselves, how we culturally wrap our heads around the natural qualities of our earthly system. Now, the Earth's sphericity, or its overall shape, is not a modern concept. Over 2 millennia ago, the Greek mathematician and philosopher Pythagoras determined through observation that the Earth was a sphere. His ideas and his mathematical models became part of a system of study known as geodesy, or the science that includes the Earth's shape and size through survey and mathematical calculation. As time progressed, mathematicians realized that the Earth expresses an equatorial bulge, and its polar oblateness is also a phenomenon. These were universally accepted and confirmed when we began to apply satellite observation, but this truth was first recognized by Sir Isaac Newton. Newton's studies, along with what we have learned since then, have become part of what is referred to as a geoidal epoch. This is a part of time, a period of time, in which mathematicians and researchers recognize that the Earth has a geoidal shape, that it is a geoid. Now, to understand the nature of this shape, you have to imagine the Earth's shape as one defined by a kind of sea level. We know that there are aspects of continental bodies which far exceed in elevation sea level. But in terms of how we will mathematically understand this, we have to look at the planet as being almost like water world, a place where only water exists and where we are measuring the shape of the planet in relation to the surface of bodies of water. Now this surface, because it is composed of water, would be shaped by the balance that exists between the gravitational attraction of the Earth's mass and the centrifugal pull that is caused by the rotation of the planet. Given what we would see if we were to create this imaginary world, we would have an object that is not a sphere. We would see this geoidal bulge at the middle as it rotates, and we would see that oblique kind of collapse pole to pole in that same rotating object. Our understanding of this geoidal shape and our ability to put aside the idea of sphericity has allowed us to be much more accurate in terms of how we map the planet and how we locate ourselves within that mapping design. Let's take a moment to travel even further back in time to better understand where these ideas initially were laid out. And we'll start with really the first geographer, who is somebody I introduced you to in an earlier portion of this lecture series, Eratosthenes. Today we recognize Eratosthenes as the first person to estimate the Earth's polar circumference. He served as a Greek librarian at Alexandria in Egypt during the 3rd century BC. It is said that local travelers visited Eratosthenes in Alexandria and told him that on June 21st, they noted that the sun's rays were shining directly at the bottom or into the bottom of a well in Cyrene in Alexandria. Eratosthenes, from his own measurements, knew that the sun's rays never were directly overhead in his location. June 21st, as you know, is the longest day of the year in which the sun was at its northmost position. So he conducted an experiment. In Alexandria at noon, he measured the angle of a shadow that was cast by a ceremonial obelisk, one of these perpendicular columns that was very often used to record history. He knew the height of the obelisk and measured the shadow cast from its base. Using the principles of geometry and right triangles, he determined the angle of the sun's rays in Alexandria. And he found that at noon, the angle was 7.2 degrees off from being directly overhead. At the same time, in the well at Cyrene, the angle of the sun's rays would have been 0 degrees. Geometric principles told him that the ground between the two locations formed an arc on the Earth's surface that was equal to the angle of the sun's rays at Alexandria. Since 7.2 degrees is roughly 1/50th of the 360 degrees of the Earth's total circumference, the distance between Alexandria and Cyrene must also represent 1/50th of the Earth's total circumference. Meaning if you take 360 degrees and you divide it by 7.2 degrees, you get 50 degrees. The next thing that Eratosthenes did is he determined the distance between the two cities, or the 2 points, in his mathematical model. Now, at the time that he was working, cartographers used stadia to measure distance. 1 stadia equals approximately 185 meters. So what did he do? He multiplied 5,000 stadia, which was the distance, by 50 to determine that the Earth's polar circumference is approximately 250,000 stadia. If we are to convert this into our own units of measurement, we would see that his measurements gave him roughly 46,250 kilometers, or 28,738 miles, which is very close to what we know to be the circumference today. So Eratosthenes, in a sense, as a librarian who enjoyed geometric principles and applying math, was able to determine that the sun was interacting with a sphere, and that during the summer solstice, when the planet is closest to the sun, certain parts of that sphere will have direct sunlight, while others, because of the shape of that sphere, the shape of its surface, will have indirect kinds of relationships with the sun's rays. Then, given that Earth-Sun relationship, the shape of the Earth itself, and to a lesser extent the shape of the sun itself, he was able to estimate the overall circumference of that sphere. Now, keep in mind, he did not recognize that it was not a sphere but a geoid. He was before the geoidal epoch. However, through the application of geometry, he was able to verify that we were living on a round object, a sphere. And that given that shape and our understanding of that shape, we would be able to map locations and places upon it. And it's these principles that lead us now to our modern coordinate system. We'll be using this coordinate system throughout the remainder of the course. So our modern coordinate system in geography is a scientific system for spatial measurement and location. It is associated with the ideas of the first century geographer Ptolemy. There are 2 general concepts that we will associate with this system, the first of which is latitude. Latitude, in this case, is defined as the angular distance north or south of the equator. It is measured from the center of the planet. On a map or a globe, the lines designating angles of latitude run east and west. They are also running parallel to the equator, and the equator is given the declination of 0 degrees of latitude. It falls directly in between the north and south poles of the planet. So given this, latitudes increase in value as you move away from the planet, either in a northern or southern fashion. The North Pole is at 90 degrees north latitude, and the South Pole is associated with 90 degrees south latitude. Each line on this diagram that you see connecting points of latitude is called a parallel. On maps, the latitudinal angles will be associated with the names of latitude, while the parallel names are associated with the line that you see depicting all of those different points of latitude. Both associations of angles and associations of parallels are describing distance in this case away from the equator. So as an example, 49 degrees north latitude is the 49th parallel. The 49th parallel is important in the Western Hemisphere, for it forms the boundary between Canada and the United States. This boundary extends from present-day Minnesota to the Pacific Ocean. Latitudes are also important, and of course the parallels that connect them, when we are describing natural environments. These natural environments will differ dramatically as we move from the equator to the poles. The differences result from the amount of solar energy that these regions are receiving because of their latitudinal location, and because of the particular season or time of year which those recordings are being taken. In geography, we label these latitudinal geographic zones. Each zone has its own unique ecological qualities. So we recognize equatorial zones, tropical zones, subtropical zones, mid-latitude zones, subarctic, subantarctic, Arctic, and Antarctic zones. Particular parallels become important as we begin to better understand these geographical zones. The Tropic of Cancer, for example, which lies at 23.5 degrees north, and the Tropic of Capricorn, which is a parallel lying 23.5 degrees south, become important when we look more closely at the Earth-Sun relationship. Why? Well, they are the most extreme north and south parallels that experience perpendicular or direct overhead rays from the sun at noon. As is the case with our example, looking at Eratosthenes and how he was estimating the shape and size of the planet, these particular parallels become important. When the sun arrives overhead at these tropics, these tropical locations, it marks the first day of summer in each of the hemispheres. The next important piece in this coordinate system is the concept of longitude. Longitude is an angular distance east or west of a point on the Earth's surface. It too is measured from the center of the planet. On a map or globe, the lines designating these angles of longitude run north and south. The lines that connect all the points of angle, in this case longitude running north and south, are meridians. So a meridian runs at a right angle to a parallel. So just as we saw before, the term longitude refers to an angular measurement, while meridian designates a locational line. And both terms designate or indicate a distance from an arbitrary 0 point, in this case the prime meridian. The prime meridian, as you can see designated or depicted here, is a meridian that identifies a 0 point, 0 degrees in this case, east or west. We recognize the Earth's prime meridian to be that line, that locational line, which passes through the Old Royal Observatory in Greenwich, England. This location was established by a treaty in October of 1884.